Welcome to Closing the Loop, podcast hosted by Lakeside Process Controls. We're connecting you with experts, end users, and suppliers in industrial automation industry. My name is 𝗬𝗜𝗠𝗣𝗧𝗜, Business Unit Lead for Measurement Solutions and host of today's show. Each episode will feature guests from Lakeside, Emerson Automation Solutions, or end users, and we hope that these conversations, we can close the loop on your current knowledge and the latest and greatest information in industry. We want to help educate you, provide you with ideas for improving efficiency and safety throughout your facility. And with that, I'd like to introduce you to today's guest, none other than Saverio Aloe. Saverio, welcome to the show.
Thanks, Justin. Thanks for having me. This is great. Very exciting.
And it's aloe?
Yeah.
Aloe?
For the most part.
For the most part?
Yes.
Well, that's fantastic. So, Saverio, this is not your first podcast, as I understand.
That's right. It's my second. I did one about a year ago. That was a virtual podcast with one of our counterparts, Ari Mason in the U.S., yes.
And, you were not 6 inches apart.
No, it was like 3,000 miles apart.
A little bit further apart.
Yeah.
Well, hopefully this one will live up to your expectations. So why don't you introduce yourself to the audience today? Kind of who are you? What's a little bit of your background?
Sure, yeah. So I'm born and raised in Montreal. Went to school there, went to McGill, studied engineering like a lot of us. I grew up, loving hockey and good food, being Italian and so forth, but...
So wait, are you a Habs fan?
Oh, I'm a big-time Habs fan. Not only a Habs fan, I made sure my kids are also Habs fans.
They're indoctrinated?
So they're totally indoctrinated.
And they're living in Toronto now?
Living in Guelph, yes, but they're totally fine with that. I did become a Blue Jays fan, I'll admit that. Habs is in my blood for sure. So.
Well, I think with that, we probably lost about half the audience members there. Maybe we'll edit that part out, okay, Saverio?
That's why I said I'm a Blue Jays fan, try to keep those
okay, fair enough.
in there, right? So, basically been in this industry since day one. Out of school, my first job was in a small valve company, and then a larger valve company in Montreal called Valan, and I was an Emerson customer. Excuse me, pretty much from the beginning, and then migrated over to Emerson for 15 years in the actuation space, and Lakeside was a customer and account for me for many years until less than a year ago, decided to take an opportunity here at Lakeside Controls and join this great team. So yeah, I've been a valve and actuator guy pretty much all my life. I'm not sure if that's a good thing, but sometimes it's exciting.
Well, you're the right person to talk to about that. See, I know very little about valves and both actuators, so I think it's going to be good. I'm going to learn a lot.
Good.
Hopefully the audience learns a lot. So you've been at Lakeside less than a year. Wow, time flies. I feel like you've been here forever.
I feel I've only been here a couple of months, but yeah, it does fly, definitely. But,
now, I do recall you did some training, maybe it was a few years back. I feel like that's probably when I first met you. And people keep talking about the Bettis bus, riding the Bettis bus.
Yes.
What is this? Before we get into what valves are, but what's this Bettis bus? Because I hear about that a lot. I see videos of people riding the Bettis bus.
I guess it's just kind of the cultural thing is, you're a Fisher person or you're a Rosemount person, and if you're into actuators, you're a Bettis person. The color is iconic. The brand, it's probably the best known brand in the industry, right? So I think
and it's orange, or it was orange.
It's orange.
Still orange.
It's a specific tint of orange. I think it's changed over the years, but yeah, if you see something in the field and it's colored orange, it's most likely a Bettis actuator.
And they're sometimes massive, as I understand. So that's also, I guess, you can literally ride them. You can literally sit on them if they're that big.
Absolutely, they can be the size of a small school bus, which is close to that color. So I think that's part of the whole sense. Bus.
Okay. Oh, well, there you go. Yeah. Now you know. Okay, so let's actually, I think it makes sense to start with isolation valves, because that's obviously tied into actuation. First of all, what is an isolation valve? What are they used for? How does it differ from a control valve? Yeah. Pretend I know nothing.
Yeah. Well, pretend you know nothing. An isolation valve is a component that stops or isolates flow of anything. You use them in your sink in your house. You use them to stop flow for water coming into your house or steam or gas. And in a facility that makes or processes anything, there could be hundreds or literally thousands of valves. So it does control in the stems in the sense that it stops and starts flow. But yeah, from tiny half-inch size to 100-inch size.
Gotcha.
For water control, automated, manual, so many different types of valves that serve different purposes. But I mean, it's such a common and necessary engineered component that's been around since the Roman times. That people don't think about it, but it impacts our life every day. It's a necessity of life, of process control, and it's.
And I'm thinking of the different examples. You're right, just at home that you probably have, but you would, as I understand, typically only in an on or an off state, right? You wouldn't necessarily kind of turn it halfway.
Well, typically, but not necessarily. So it is used as a crude control valve, just like at home. It's sometimes you turn the water on a little bit, so that's a partially open valve. So it does control. And same thing in the process side. An isolation or on-off valve, if you will, is sometimes used to control flow. It won't be a precise pressure control device like what we call a control valve. But often it's used for both, if depending on the application or.
Actually, that makes sense. We have a micro-motion flow demo loop, and I have a little ball valve on there, and I get it about halfway, three-quarter way, and it's like the perfect flow. So I guess that's what I'm doing. Yeah, it's not very accurate because I know I crank it a little bit further, and everything goes off and stops working.
That's right.
Okay, that makes sense then. So, but there are different types of isolation valves, right? So what would be the ways to classify them?
Yeah. So I guess one thing to keep in mind when you're talking about, let's say, applications people or inside sales, for the most part, they don't have to decide on what type of valve. That's usually decided by a customer or an engineer at the front. Same thing, I know we'll talk about actuators, why electric, why pneumatic, we can talk about that, but usually that's determined beforehand, and then you just got to decide what's the best design or version of it. But it really varies on the application. Some valves are good to do some control, some are not. One thing people don't realize is valves are allowed to leak. Most valves can leak. They're not necessarily, I won't say designed to leak, but they're allowed leakage. So if you want a valve that does not leak, that could be the difference between a cheap valve and a costly valve. So like everything else, it's based on cost. You pick a valve that does the job for the least amount of cost. So, for example, butterfly valves and gate valves are low-cost devices, to serve a purpose. If you can get away with that, a ball valve might be 10 times the price of a butterfly valve. But butterfly valve is limited pressure, temperature. It can't handle slurries or dirty surface. It's got a big obstruction in the middle, so it doesn't have a high CV or would have a high pressure drop, right? So once you start adding these requirements, you start getting into, higher tier valves. A triple offset is really a butterfly valve, but it's a zero leakage valve. It's almost like a cross between a gate and a ball valve. And then I think, I know you like the knife gate valves.
Yeah, I'm a big fan of those.
Those are pretty specialized, even though they allow for process to come out of them or discharge, which is kind of odd. But they can handle basically rocks and what have you flowing through them and still be able to shut off, right? And then, like you said, do they have to control? Do they have to move fast? If they have to move fast, you usually want what's called a quarter turn valve, like a ball or plug or butterfly, which means it only turns a quarter of an operation, so you can do that pretty fast. A gate or a globe or a knife gate, that takes many turns of the stem. Just like at home, if you're turning your water hose, you notice you got to turn it 10, 12 times. So that takes longer to operate. So you're not going to use a gate valve to turn in a quarter of a second or a second, right?
That makes sense.
And then it depends if you want to automate it or not. Some lend themselves more to automating quarter turn, for example, as you can imagine, if you would have got to turn something a quarter of the way, it's easier to automate. If you got to turn something 100 times, then that might be a little more complex. So it's a combination of specs, requirements, performance, size, and then cost. At the end of the day, which the engineer or the EPC will decide what type of valve can do this job for the least amount of cost, taking into account automation requirements, right?
Yeah.
And
So all of these will isolate.
Yeah,
okay.
all of them, one way or another.
All
another. Will isolate flow. Some will leak, some more than others. But if they're selected properly, they should isolate the flow.
Gotcha.
Yeah.
Yeah, so you did hit on a fun one. I seem to really like the knife gate valves. I don't know why. There's just something about them that just seems very simple. It's just a giant knife, cuts off the flow.
Yeah.
Something that you mentioned that I learned was this concept of discharging knife gate valves versus non-discharging. Maybe you could talk a little bit about that, because I'm maybe because of my experience of mining. You walk through some of these processing plants and they're really dirty, and I thought miners were just dirty, but it turns out it actually might be because of your knife gate valve. Is that correct?
I think it's a combination of things.
Oh, okay.
Again, it's like everything. It's pros and cons, right? So you're flowing with a slurry. A slurry is usually water, liquid combined with solids. So if you can imagine, ore or rocks and giant particles, how do you cut the flow off of that, right? So basically you need a mechanism, like you said, a big gate that's sharp, but it can't trap anything in the valve seat, right? Because if you try and do that, it'll just build up and sit there. So basically it pushes some particles or slurry right outside the valve and onto the ground or into a bucket. It's not a chemical service in the sense that it's dangerous. It's not ideal, but it's one of those pros and cons, and so you need somebody every once in a while to clean that up.
It almost reminds me of like a French guillotine, right? Like that's for those of you who don't know what this looks like, just picture a guillotine, but it's now a valve.
Well, so in French, a gate valve or a knife gate is called a guillotine valve.
Oh,
so there you go.
There you go. Oh, so when you say gate valve, it's the same thing as knife gate valve.
It is. Usually a gate valve just uses a larger closing, mechanism or gate, whereas a knife gate is basically a guillotine. It's thin, wide, sharp.
Okay. Okay. So you can have different styles depending on if it's a slurry or maybe just a water line.
Water.
Or steam.
You can have knife gates on 1,000 degree, 2,000 psi steam service in a power plant. Right. They're very good for that. For that type of service.
Yeah, I imagine, because it just cuts it right off. So then how does a non-discharging knife gate valve work? Like, where does the particulate go then? If how does that work?
It stays in the seat or in the body, right? So that's why gate valve, a traditional gate valve, you asked about which one to pick, is not very good for a slurry. So, you would use it for power applications, for water, for steam, even for oil and refining. But if you don't want to discharge and you have a dirty or slurry service, you might use a ball valve, for example.
Gotcha.
Or a different solution for that. So knife gate valves are very specific, mining and pulp and paper. Outside of that, you don't see them too often.
Gotcha.
Because of that.
Okay, so in a slurry, you probably wouldn't be able to get away with a non-discharging knife gate.
Not if it's a high slurry, right?
Yeah.
So usually we classify based on particle size and percentage.
Okay.
Right, a conventional versus a discharge. But when you're talking about 70% slurry, very large particles, there's really only a couple of valves that can do that. And if you don't have a discharge valve, it'll probably clog up or seize.
Or leak through or not fully shut. Okay.
Yeah, it won't shut. So
it's interesting you classify a high slurry percent around 70, because that's good. Our definitions are similar. When I'm thinking a mag meter, I'm thinking high concentrations of solids. I'm thinking above 50%, 50, 60, 70. It's typically a different mag meter solution when you get to those levels. It's good, though, because depending on who you talk to, they have different definitions of high percent, especially like food and beverage, right? Totally different percentages than pulp and paper or mining.
Yeah, everybody has their own, I guess, rule of thumb. And that's something, I mentioned, a customer may tell you that they want a knife gate, but they may not say what kind of design. They'll just say, I need a knife gate. Here's the pressure, temperature. Here's the slurry. Often we got to go back and say, well, what's the percentage like? Because if you don't need a discharge valve, we'll probably just go with a conventional, which doesn't discharge, and it's also less expensive by design. Right. So you always try and pick, again, the best solution for the most reasonable cost, right? Since there's so many.
So if I know I need to isolate my process, when I reach out to Lakeside or I reach out to you, what sort of information are you going to need in order to pick? Like, let's say I don't have an isolation valve and you get to pick from all these different ones. What do you need to know?
We'll use a typical instrument type data sheets. So something that'll tell us the process conditions, definitely, do they need a full flow capability is one question.
Interesting.
Right? Because, a gate valve or a ball valve will do that. A butterfly valve may not, or you can have a reduced bore. So what are their expectations? Like a control valve, you have pressure drop, obviously, so that's not a question. So flow rate or that type of sizing doesn't apply to isolation valves, but you need to know if pressure drops an issue. And then obviously pressure, temperature, what's going through the valve. Is it automated is one. Like I said, if it's automated, a quarter turn is a little easier to and less cost to automate, right? You can automate a knife gate or a large gate valve, of course, but you're kind of limited. But, sort of the typical process conditions you would find in almost any other instrument is the basic questions we would ask. Yeah.
Okay, that makes sense. And you can automate all of them.
Pretty much any isolation valve can be automated. Some easier than others, but basically any valve can be automated.
Oh, that's pretty cool. Yeah. Now you mentioned full port ball valves, and that's something that kind of resonates with me because we use ball valves in instrumentation sometimes to help isolate. So, for example, sometimes our DP flow meters, we have a retractable assembly for an annubar. And that we need to make sure that we have a full port ball valve because we want to be able to remove that annubar. So are there different types of, there's less than full port or, when would you use one or is it just maybe a cost conversation?
Yeah. So let's say ball valves, for example, most ball valves have a full and regular port version.
Okay.
And the regular port is one size smaller. So if it's a 6-inch ball valve, the port is only 4 inches. So the cost is closer to a 4-inch valve. But you're not going to get the flow to that. So one typical application is gas, so natural gas transport. You would think that gas is easy to isolate. It's just gas. You can use like a cheaper valve, like a butterfly or a gate. But the reality is you want very little pressure drop, right? You want whatever you're pushing through that line, you want it to keep going. And you also want it to seal very well. You don't want any leaks through the seats. So ball valves are typically used, even if you're talking a 36-inch or 42-inch, and it could be, $100,000, where another valve could be, $10,000. But that's for that application. That's the only valve that really serves the purpose and does everything it needs to. And the gas industry tends to have more money, so it's not always.
I see.
That's one thing we deal with. If you're dealing with water, wastewater, and pulp and paper, they don't have the cash to I guess support any solution.
That makes sense. And now this might be a self-serving question too, but when I ask for a full port ball valve, does it matter the manufacturer? Is that a standard thing? It's like no different than asking for a Class 150-pound flange.
Typically it is. It is if it's we follow typical standards, ANSI, API, and generally, everybody is slightly different how it's built. But when you're talking about full port, reduced port, that's pretty consistent. Butterfly valve, everybody will have a slightly different. The disc is a different size, or the CV or the flow rate. That's different. So you'll get that question. If you're offering a butterfly valve, but a ball valve should basically be like a piece of pipe. If it's a full bore ball valve, there should be no pressure drop.
Gotcha.
So that's a pretty consistent spec through.
Okay, that's good to know. Yeah. So we talked about knife gate. That's the guillotine. Ball valve, at least to me, is pretty obvious. It's a ball that rotates that allows full port possibly or nothing. So then let's talk a little bit about butterfly and triple offset because I think I want to make sure I'm visualizing that and I understand the differences between those. Can you explain them a little bit more?
Yeah, so a butterfly valve is really the claim to fame is it's a very inexpensive design to isolate, especially once you get into large sizes. One, if you can imagine, you think of a ball valve, you have a ball and you have a body that has to enclose that ball valve. So let's say an 8-inch ball valve might be 12 inches long, just because it's got to hold that. 12-inch butterfly valve might be 2 inches wide. So right there, you can see the cost. Then the material, you got a ball versus a small disc. So that's what I was saying. A ball valve might be 10 times the price. But let's say now you have water or air or steam. So think like HVAC, water, wastewater, utilities, where you don't really care about pressure drop necessarily, and you're not talking high pressures or temperatures. You're going to see a lot of butterfly valves because, again, the cost of the valve is a fraction of another solution. It's very easy and inexpensive to automate a butterfly valve because you don't have a lot of torque, right? You need force, just like you got to turn it by hand. Trying to turn a 10-inch ball valve by hand versus a butterfly is also night and day. So if you can imagine,
Really?
An actuator is going to be considerably smaller. So at the end of the day, the cost, the weight, the installation cost, the maintenance for a butterfly valve is very low.
So before you talk about triple offset, so just so I understand, so when we have a butterfly valve, you have the stem basically in the center of the valve, and then you have the disc that kind of rotates around that center point. Yes. So I guess, is that why it's easier? Because once you start turning it, the flow actually might try to help you open it.
Yeah, it does. The flow assist, you have, I guess, hydrodynamic forces in effect. But at the same time, a butterfly valve can move on its own. If it's left in the middle, unless it's locked in place, the flow can move it, whereas that can't happen with a ball valve. A ball valve is static unless it's somebody intervenes and opens it up or closes it, being manual or automatic.
And because as you turn the ball valve, it kind of cuts through the flow. It's almost like a sideways curvature gate valve in a way.
But it's also, you have a lot more friction between the ball and the seats. You have a lot of friction, so you can't the flow cannot overcome that friction, which is a butterfly valve is a thin disc, right? You have a lot of force on that disc with flow and not a lot of contact with the seat. So it can kind of move on its own. Right?
Okay,
So,
that makes a lot of sense actually. Yeah. And then triple offset, I guess, is the same thing, but it's offset 3 times.
It's offset 3 times. Really, the third offset is the seat is not round. The seat is actually oval, so it's actually a wedge. If you think of an example like a door, or airplane door especially, if you think it kind of at the end. It doesn't make any contact except right at the end, and that's what the triple offset. So the reason for a triple offset, I mentioned, butterfly valves are cheap, but let's say you have a service, again, 800 degrees, high pressure. Butterfly valve is no good for that. It just can't handle it. So you need to put a large gate valve. But now, if you can have a butterfly valve that's all metal inside, it can handle 800, 1,000 degrees, and can provide no leakage. Now it's a different story because, again, we're at a valve that is considerably smaller, less weight, and considerably easier and cheaper to automate. So the butterfly valve is one of those designs that over time has replaced other solutions, and a gate valve is a classic example. Whereas in the past, the gate valve would have been used for isolation of steam, condensate, tank farms, isolating fuels and oils. The triple offset now is it's taken over a lot of those applications, especially if it's automated. Again, the disadvantage is like a butterfly valve. You have an obstruction in the middle.
Yeah.
You're not going to get that flow rate. But if you can live without that, the triple offset becomes a pretty interesting solution, and claim to fame is zero leakage.
Yes, that's the big
Whereas
point, right?
you can't get that with a gate valve. A gate valve right off the bat is allowed to leak. So if imagine on a tank, if you're isolating fuels, that's not so good, right?
No.
So that's the main purpose of a butterfly valve. But it's one of those valves that a customer might have an application or a replacement, and you would actually try and potentially talk them into the solution. because it's better. They may not be aware. Whereas
Gotcha.
almost every other case, they ask for a gate or butterfly. You'll give them that, just the best type that you can find. Right?
Okay.
Yeah.
And so the brands, as I understand, 𝗦𝗧 for triple offset, Keystone for butterfly, KTM for ball valves, and Clarkson for knife gates.
That's correct. So, and like 𝗬𝗠𝗠, these were Pentair brands that were acquired. They're like, the top brands in the industry.
Gotcha.
Right? They're very well known. If 𝗦𝗧 was the original triple offset, everybody has basically copied that.
Gotcha.
Clarkson was the original knife gate valve. KTM's been around for 100 years.
Okay, yeah. Oh, wow.
So it's very well known. And Keystone's the same thing. We have Keystone valves, 72-inch, 86-inch installed at the nuclear plants from the 70s.
Wow.
And they used to be made in, I think, Woodstock back in the day.
Oh,
so
cool.
a lot. The legacy and the history of the brands that we have is pretty amazing, and I guess makes it interesting, more fun to sell, right?
And for those listening who aren't in Ontario, it's Woodstock, Ontario. It's
Ontario.
a different Woodstock. It's not the. Unfortunately,
Yeah.
I mean, it's a great place, but
Yeah.
it's not like the Woodstock.
Not
right?
the Woodstock, not 69 Woodstock.
Yeah. So I think it's pretty obvious if I see a knife gate valve, maybe even sometimes when I look at some of the others, but like, how do I tell the difference just by looking at it? Like, can I, or do you have to be kind of trained?
You have to have a bit of knowledge. I mean, a butterfly valve's easy. It's thin, right? It's just,
okay.
You can, same thing with a knife gate, but knife gate, you'll be able to tell because it's rising versus just quarter turn, right? So those two are pretty easy. Ball valve, also, it's wide. It's got a fat kind of body.
Yeah. Okay.
Gate valve is usually somewhere in between, not as wide, right? And usually it's got a kind of a V shape in the middle, which is where the wedge or the gate falls. And then a globe valve, if you're familiar with the Fisher, it's kind of like a swoosh body.
Yes.
It's not like a straight through.
Yes. It's got a seat that plugs.
Yes,
versus,
it's got a plug seat. So it's, obviously you need a little bit of background and training, but once you've seen a couple of them, it's pretty easy to spot one versus the other. Yeah.
And so I feel like it's fair to say besides knife gates, most isolation valves you turn. I believe there's some control valves that also turn as well, right? But is that one way? Like most times, if it's turning, kind of that's a way that you can identify if that's isolating something or not necessarily.
Usually, but a knife gate valve turns too. So if you do it by hand, it's just a wheel.
Oh,
Again, imagine like your water hose. It's a little wheel that you're turning. You're just turning many times. A quarter turn might have a gearbox on it, and a hand wheel might be on the side. But you can see if there's a stem coming up through it or not. Well, you can tell, what it looks like. But, a small valve might be a lever, like a butterfly valve or a ball valve, just because, whereas even a ball valve, even though it's a quarter turn, you need so much torque once you get to a certain size. You need a gearbox as a mechanical advantage. So you're still turning a wheel to turn a gear that only turns at a quarter of a turn, right?
Okay.
And that's why you get into automated valves. The bigger the valve, the more the reason to go automated, because you don't want somebody there taking an hour and a half to open and close a valve. And it's not uncommon. Yeah. Well, I mean, back in the day, one thing that's interesting we get to do is we go to plants that are 30, 40 years old, and now they say, well, we want to automate this 40-year-old gate valve, which is a challenge. But that's something we're good at. Anybody can sell an actuator, but to go in and modify a valve to now put an actuator on a 40-year-old valve, because like I said, it used to take somebody 2 hours to operate that. Now maybe they want to do that once a week. You retrofit actuation on that. That's a big part of our business, especially on the electric side.
Okay. Yeah, that's actually a really good segue. So it seems like we understand the isolation valves, and you kind of hit on the problem is that, we're in the business of closing the loop, hence the podcast name, right? We're looking at automating things. So maybe talk to me a little about actuators, what their jobs are, maybe some of the different types.
Yeah. So similarly, more often than not, we're not expected to decide between, let's say, an electric, pneumatic, and hydraulic. That's predetermined, but there are a lot of reasons to pick one versus the other. Depends on the application, depends on the valve type, also the location and what you're trying to do. So, for example, we talked about gate valves. They're very difficult to automate pneumatically, but electrically it's quite easy. I mean, electric actuators are basically designed to operate gate valves, to use gears to turn many times,
Gotcha.
Electric power, but they don't operate very fast, electric actuators in general. So if you want something like an emergency shutdown or a fast-acting pneumatic or hydraulic is a better solution. One thing in the automation world for us is fail-safe requirements. So if you lose your main power source or your, be it air or hydraulic, if it needs to go to a safe position, you can't typically do that with an electric. There are some designs, but for the most part, using a spring or sort of like a control valve, a pneumatic or a hydraulic, that's kind of the go-to. But then is there air and hydraulic power available? That's the thing when you're designing the plant or the valves, you got to take into account not just the cost of that assembly. What about the utilities? How many compressors do I need? Where is that compressor? One thing we're seeing is because electrics have come a long way, we can use them now for control and fail-safe to a certain extent. Customers are moving to electrics for outdoor applications, and outdoor in Canada means cold. Air is not the best when you're at minus 30 or so degrees, so we're kind of seeing a migration to more electrics because of that. Getting air compressors outdoor or semi-remote locations is difficult. Emissions is one if you're using gas or you don't want to waste air. Electrics is also the way to go. And also, with designs these days, you can use them on control valves. You can use them for fail-safe to a certain extent. So electrics is just gaining momentum and I guess market share, if you will, versus the electrics and hydraulic counterparts.
Yeah. So you kind of touched upon a little bit, normally open, normally closed. That's important to understand, right? Because as I understand, it's important to make sure, are we in a constantly energized state or non-energized state, especially when it comes to fail safety, right? So, I guess if you're normally open, you want to fail close, you would want it to not be energized, or how would that work?
That depends on the controls and the solenoid. It's more the mechanical arrangement. So let's say you have a valve that's isolating a tank and it's open, but if you lose power, you want to make sure that doesn't drain or you want that valve to close. Yeah. So mechanically, the spring would close the valve, but electrically, you'll have a solenoid that's always energized, and if that loses power, it'll also trigger an event, right? So it's kind of a combination of mechanics and electrical control once you get, and that's the other difference with pneumatics and electrics. An electric actuator kind of encompasses all the controls built into one unit. Pneumatics is more of a plug or glue on. I start with an actuator, now I add a limit switch or maybe a positioner, and then I have to add a solenoid, a filter regulator, a relief valve maybe. It's a little more complex in the sense that it's all, not always, but more custom assembled, whereas an electric is just, check off the box of options and everything comes in a box and then you just attach it, right? So for that, it makes it easier to specify, to control the cost, to a lot less labor involved.
Gotcha. Yeah. So for an actuator, I guess there's different types depending on, I don't know, let's call it the fluid, although electricity is not really fluid, but there's the fluid you have to actually actuate. You also mentioned something called a positioner, which, to my understanding, exactly as it sounds, it lets you know the position of the valve. Is that something you see with isolation valves? Because I always thought about that with control valves mainly.
Yeah, so a positioner lets you position the valve at a certain point in the stroke, and it can also feedback position continuously. Most isolation valves are on-off valves. They're open, they're closed. You send the signal to open it, you send it to close it, and then you want to know when it's open or closed. In that case, you don't need a positioner. But like we mentioned before, sometimes you want an isolation valve to control, even if it's crudely. It could be, I want it to go to 25%, 50, 75, ramp up. Then you might use a positioner and like an analog signal to say, to go to this position, 10 milliamps or what have you. And then it'll feed back and say, hey, I am actually at this position. So it's a small percentage of isolation valves, but like I said, in some cases, either you use an isolation valve as a control mechanism just because it's considerably less expensive than a true control valve, or it has to do both. And some can, like a butterfly or triple offices is a good example. That's why, the Fisher does have butterfly valves for control, because it's kind of the first step where the butterfly is the first step of control in the Fisher control valve world. That's kind of the best in the isolation valve world, so it kind of crosses over. But yeah, it's kind of so sometimes you don't need an isolation valve plus a control valve. That valve will do the same thing, just not as well as a Fisher.
That makes sense. Yeah. Do you need an actuator to use a positioner?
Yes.
Okay.
Absolutely.
Yeah, so you can't just put it on a manual and what okay.
Yeah. So if it's if it has a positioner, it absolutely has to have, and generally it's a pneumatic for the most part.
And so let's say we already have an isolation valve. We're looking to automate that, and electric, pneumatic, hydraulic, it doesn't really matter for the customer. Do you have a heuristic that you follow? And I know another piece to consider is mounting. I believe that's probably difficult as well. Like, how do you mount all these different sizes? Yeah. Talk a little bit about that, what you kind of work through.
Yeah, well, for sure, if you're automating an existing valve, that becomes more complex. But you need some expertise. Lakeside, we tend to be good at that because we have people who know how to do the mounting. A quarter turn valve is usually easier because it has a custom bracket and interface, so you can take any existing valve, design the bracket and coupling to mount it, because it's not a direct connection, so it lends itself better. A gate valve or multi-turn is a little bit different because the stem has to connect directly into the actuator, so you can't just put a bracket and something in between. That means you might have to weld on a flange on an existing valve.
Oh, wow.
So it's a little more complicated. It's doable. That's why I said, multi-turn gates, globes are not the best for automating, just because there's some nuances. Whereas, a ball or butterfly valve, even if it's in the field, just, if you know the measurements or the dimensions, we can build a bracket and a coupling and then mount a pneumatic actuator. It's a little easier to do. But like I said, we've done like 40-year-old valves where we've had to do custom adaptation for an electric actuator, an old gate valve. So anything's doable, right? Yeah. But just some are easier than others.
I feel like, too, sometimes, depending on the valve, it might even just be more cost-effective to just replace the valve and get the actual, than just trying to mount it onto the existing isolation valve.
100%. And this is where you would suggest a different technology. So if I have a gate valve, like a 10-inch gate valve, and I want to automate it, we'll tell the customer, hey, if we put in a triple offset or a butterfly with an actuator, that's going to be less expensive than just trying to put an actuator on the existing. And now it's going to be a zero leakage valve, or it's going to be less weight.
And it's brand new.
And it's brand new. And it's brand new. Yeah. So that's, in those situations, that's where you kind of you can upsell and change technologies for sure. Yeah.
And they could also just reuse that gate valve somewhere else, right? Like, it doesn't necessarily just go bad like that.
Exactly. Yeah.
Wow.
And they're used for tons of applications, so you can reuse that valve.
Okay. Yeah. Now, in terms of the actual actuator technologies, right now, I guess the split I'm seeing is between pneumatic, hydraulic, and electric. What would you say is the most common? And would you say that that's changing? Is there a shift towards electric, let's say?
There is a shift. For sure, pneumatic is by far more common because there's a lot of small valves, small balls, small butterfly valves in process control. Those are easy to automate. Pneumatic is the most common. Hydraulic tends to be large valves, mining, maybe offshore, just because HPUs or hydraulic power units are messier, they're costly, they're harder to maintain. But hydraulic, as you know, you can get a lot of force out of hydraulic. So usually that's reserved for large valves, pipeline valves, for example. Electrics are more common in multi-turn, so gates, globes.
Okay, yep.
Just because they're easier and less costly. So a power plant or a wastewater treatment plant is going to be 80% electric.
Gotcha.
Flip side for maybe a refinery or food and bev or something like that. But there is a trend to move to electrics more and more these days, mainly because change in technology. So previously, an electric was an on-off device. Now we have designs or technology where we can actually do fine control. We can do fail-safe, mechanical fail-safe, which wasn't available before.
Mechanical fail-safe with an electric actuator.
Yeah, so a spring with an electric.
Interesting.
Yeah. So that's a very, very popular product, and that spans across a lot of industries. We have that technology in our portfolio, and then you get into electrification due to outdoor, semi-remote, reduction if you're using gas to power your actuators, which was common, in the past. Once you get into that, then electrics also make sense. Or if you want to get rid of compressors because it's costly to maintain or the location is difficult. Yeah. Again, because of the combination of control and fail-safe and everything else. Now that you have EPCs and customers who, in a greenfield project, they're starting with trying to go all electric versus, or at least
really?
looking at that. Yeah, which was kind of interesting. In the past, it was either 90% pneumatic or a combination, but now in some industries, they're looking at potentially going all electric if possible.
Wow, that's amazing.
Yeah.
And now, correct me if I'm wrong, electric has existed for a while. Yes. It's just these recent advancements that have really kind of pulled it forward. Okay.
Yeah, advancements, in technology, but also a change in, could be environmental sustainability. That's also added to that. Reliability. In the past, a remote actuator would have a battery backup. So you'd have somebody checking on batteries every few days, and whereas now, again, I mentioned spring return. That's kind of changed the game for electric actuators too.
Oh wow, okay, that makes a lot of sense. And then with the pneumatic side, you mentioned something about leaking. Can you talk a little bit about how that works? Why is that a concern with pneumatics and not electric or hydraulic?
So I mean, with pneumatics, you have potential for loss of air. So long-term utilities, if you look at the cost of a device and an automated valve, an electric might be two times the cost. It depends. And you'll say, well, that doesn't make sense. Why would I go electric? But if you look at, the total cost of ownership, how much does air cost a customer? If you're losing so much air per hour, add that up by month, by year, all of a sudden it starts to make sense. Or repairing or maintenance of compressors. Or if you're trying to push air up 10, 20 stories, or hot water or whatever it is, you don't have those losses. Electric is electric. If you have 120 volts on an actuator, that's not going to change unless you have power outages in a remote location. Same thing with hydraulics. They're prone to leak, obviously, depending how far your power source is to the actuator, how many you have connected. So it's one of those things that you gotta kind of look at the life cycle or long-term cost of ownership. And if you do look at that, especially from the beginning, a lot of times electrics makes sense, even if the upfront cost might be higher. A
little bit higher.
Yeah.
Now, okay, so that would be if we're using compressed air for pneumatic actuator, but as I understand, there's also methods to use the process pressure itself, and or the process gas, like for natural gas.
Yes.
Is that correct? How does that differ? Why would you use that versus just using the compressed air, let's say?
Well, that's ideal because you don't need any compressors. You're basically, like you said, you're using the pressure from the process gas to power the actuator. And then you're just using maybe the solenoid or controls to open and close it to redirect it. So that's ideal because you can operate a 36-inch valve and all you need is a low-power solenoid valve. Electric would work also. However, you probably have to bring in 600 volts. You have to have that power source. And a lot of these valves are remote. They're semi-remote.
Yes.
So those are ideal. However, the downside is every time that valve strokes, you're emitting the amount of gas that you've compressed in that actuator to move the valve, and that's
it's leaking to atmosphere.
It's leaking to atmosphere. So that's an interesting point. Now we're getting into some pretty specialized applications, but we do have a special designer. Emerson does. I'll say we about Emerson because I was at Emerson a long time. And we actually just sold our first one to Enbridge. I think it's the first one in Canada. It's called an ECAT, an environmentally controlled actuator technology. Wow. And what it does is it's sort of like a hybrid between the gas-powered actuator, the gas over oil, and an electrohydraulic. It incorporates a motor and a pump. So what it does is at the end of the stroke, the motor turns on, it compresses that gas such that the pressure is higher than the pipeline, so it pushes it back into the pipeline.
Oh, really?
Yeah. So this is pretty cool. Now, it's not cheap.
No.
But as you know, they're looking at emissions control, especially in Canada.
That makes sense.
Yeah. So there's a lot of opportunity here, and not only for new applications, but if you can imagine, there's thousands of these in the field.
Yeah,
right.
A lot of leaks.
So a lot of leaks. Even though they don't stroke very often, it's still they're trying to reduce bad apples. Which ones have the highest?
Yes.
So I think we have an opportunity, mid to long term to start. The nice thing about this design, you can retrofit on an existing one. So if you have an old BDP actuator or Schaefer, you can go there and retrofit it to this new technology.
That's
and turn
really
this
cool.
into a zero leak. So yeah, it's actually pretty cool design and technology that we've been working on, and should have some good opportunity.
So, but that is probably for a pipeline or remote.
Yes.
So,
yes.
But in most cases, I think we've been talking a lot about sustainability, and I think that the electric actuator kind of fits quite well into that. Like you said, you don't need a compressor. So, can we quantify those impacts? Is there a way that we can look at that and see if you have 100 isolation valves and
you can, yeah. I mean, if we have the data, obviously, how many valves are you powering? How many compressors? It's not just you still need electric power to power those compressors. So there's a lot of energy required. How much is lost over time? So there is a lot of energy savings. An electric actuator only operates every once in a while. Doesn't consume a lot of power generally. And then the other thing for environmental control, some applications might use, let's say if you're using a control valve and you're using gas to power that, now that's always using or bleeding gas. So that's like and so those are the first ones that generally get converted to electric, right? So you can quantify it. Sometimes it's not that easy, but with the right information, right? If we knew the types of actuators, how many there are, how many compressors, and what have you, you can make a case for a reduction in energy.
Yeah, and then cost.
Over time and cost.
As well. Yeah. Wow, that's pretty cool.
Yeah.
So when you are maybe sizing or selecting an actuator, any actuator, is that something that differs in terms of the information that you need compared to, say, just the isolation valve? Like what goes into picking that and then sizing it? Like how big do you make the actuator? Right? What goes into that?
Experience, rules of thumb, standards, I guess. Well, actually, there's not a lot of standards, but it depends on the application, definitely. A gate valve, a butterfly valve, generally is not working on a very difficult service. So you don't need a lot of safety factor because you can assume that the torque or force required today is not going to change substantially down the road.
Gotcha.
Same thing with a triple offset, and the reason is I talked about that door or swinging door. Triple offset only makes contact right at the end. So torque doesn't really change through the life of the valve, and you're not going to use it on a slurry service. If you're talking a ball valve, that's different. You can have, example, mining service, where over time the valve starts to cake up. You get buildup in the valve, or a refinery service where the torque today might be considerably different than the torque in 6 months. So where you might, if we throw out a number, maybe a 20 to 30% safety factor, is minimum or standard for most valves. A ball valve could be 50%, could be 2 times. I've seen 3 times for some mining and refining services. So so you really have to know, what the application is, what the criticality is. An emergency shutdown valve, you typically want to use 50%. Why? Even if it's not a difficult service, that valve is open 99% of the time. So if you ever tried to turn a valve at your house that hasn't been open in 3 years, you know what happens, right? Yeah. So you need more. And also, because it's critical, it's got to, it's got to be able. So even though the cost of that actuator is going to go up because of that safety factor, you got to weigh the consequences and the criticality of that, right? So it depends on valve type, depends on application, and depends on safety requirements.
So it's there is a science and a math behind quantifying it, but then it's just about how safety you need to be, which is kind of, I guess, almost the art of it, right? And trying to understand those nuances. Yeah,
and I mean, if you're working on a project, more often than not, the engineer will specify their own safety factor because they've decided. If you're just working with an end user who says, "Hey, I want an automated valve," it's kind of up to you, with your a bit of knowledge to determine what's the right safety factor to use. And you got to be careful because there's also maximum allowable torques on valves. If you go too high and something goes wrong, you could damage that valve. So it's a balance between enough torque to turn that stem, but not too much that potentially you can tear it up or damage it, right?
Okay.
But
sense.
So that's why we have a lot of training going on at Lakeside with a lot of new applications engineers, and that's just one of the many subjects, right, we get into.
Well, and that last piece that you mentioned, though, was something I'm interested in, was learning more about kind of how these technologies break down over time and what the repair looks like. We get into a lot of troubleshooting with instrumentation. Maybe you could just briefly talk about what that looks like for isolation valves versus the actuators.
Yeah, well, that's a good point. We talked about the advantages of electrics and all the good things they can do these days and how they've come along. The downside is an electric actuator is a lot more complex than a pneumatic actuator. It's a piston usually and some seals. There's really not much that can go wrong, and the good brand like 𝗬𝗓 they're bulletproof. I mean, it's not uncommon to never change out a seal. An electric is different. You got contactors, you got starters, you got limit switches, you got printed circuit boards. They need a little more maintenance, and they're expected to be repaired or overhauled or swapped out every so often. So definitely, there's more maintenance involved on an electric versus a pneumatic. As far as valve goes, it depends. I mentioned like butterfly valves are cheap. The reality is they're throwaway valves. You're not going to replace a $300 valve or try and repair it because an hour of labor will make that up.
Gotcha.
Ball valve, which might be $50,000, you might repair. You might change the seats. Knife gates, for example, even though they seal against this crazy amount of slurry and solids, the reality is the sleeves, which are kind of the pressure retaining components, they wear. So those are periodically repaired, and they're designed to be easily repaired. Taken apart, you keep the main body or core, the metal parts, and you change the soft parts of the sleeves. Some versus the other, but if you would use a conventional valve, you'd probably have to throw it away.
Gotcha.
Even though it might be that's the other balance. Do you want a low cost valve that you can't repair, that you have to change every couple of years, or do you want this valve that's 2 times the cost, but maybe you only need to repair it or change it out every 10 years, right? So that's kind of the discussions and the challenge. And the same thing with our brands are high tier. They're not generally the lowest cost. But the message is often like 𝗬𝗓. That's I think the Alomatic motto is fit and forget, and that is not untrue. You put in that actuator, it is not uncommon that it will run for 10, 15 years, and you don't have to change out a part or a seal, right? Yeah.
It's just funny coming from the instrumentation world, right, where it's a lot of set and forget until it dies, right? There aren't necessarily a lot of repairs, right? If your Coriolis works until it doesn't, right? And maybe you can clean it out, but oftentimes after 10, 15, 20 years, it's eroded or corroded, and that's it, right? So totally different world. And It
is. I mean, don't forget you have some valves that not only are they large and expensive, but they're welded in. So it's you might change the actuator, but if you bury a 24-inch valve at end bridge, or if you weld in a 20-inch 900-pound valve at a power plant, they might repair them, but replacing it is incredibly costly. So there's different programs in place depending on the valve. So they got to take that into account from the beginning when they're specifying that stuff, right? Yeah.
Wow, a lot of trade-offs.
Yeah, a lot of
trade-offs.
A lot of pros and cons. A lot of trade-offs. There's so many variations, so many valve types that 3 or 4 different valve types can potentially serve the same purpose, but long term, it's a completely different story.
Wow. Well, I'm glad I talked to an expert like you. I definitely learned a lot about isolation, actuation. Hopefully our listeners did as well.
Hope so.
If someone wanted to learn more information, about either, where would be the best place to go?
Well, there's a lot of places. Internally, we got our website. If you're a Laker and you want to learn or train, we finished putting together a pretty comprehensive training program from Basics 101 to more advanced that we'll be getting into next year. That's available. It's mostly virtual.
Cool.
So you can learn basics of isolation valves, of actuators, all the different types. Obviously, it's focused around the Emerson brands, but that's available. Contact myself, either email, Teams, or you want to hook up on LinkedIn. You can definitely find me there too. But yeah, don't hesitate. I really enjoy this sort of stuff. Teaching people. I do have a lot of experience. I don't know if I'm an expert. Maybe that's a relative term.
More than me. More than
exactly.
Me. Yeah.
It's all relative. But I do enjoy passing along that knowledge. So yeah, don't hesitate to.
That's fantastic. Yeah. Well, thank you very much, Saverio. With that, we're going to close out the podcast today. Really, really appreciate it. And until next time.